And remember, we're going to kind of grade your extra credit at the end of the class session. So make sure to get those out, have those ready, have those files ready. And I'm going to have you look them over. When I say grade them, if you've done it, you'll all get the 3 points. It's just that we're going to analyze them. And we're going to try to apply a discrimination rule to figure out, so that I can figure out who did what. All right, so where are we on the schedule? We're keeping to the schedule. Today is Wednesday, September 16th. We're going to cover lessons 12 and 13 on some rules of probability, on adding and multiplying probabilities. All right, remember that, and I'm still continuing the grading. Okay, remember, September is going to be a slow grading month. End of the month and October will be a breakthrough for grading. Now, regarding the current homework assignment, that's lessons 11 through 18, and that's all due, Tuesday, October 6th. Remember, we have 2 sessions to discuss the homework, and then this homework is due Tuesday, October 6th, lessons 11 through 18, and they're on my website. All right. Any general questions before we go on? Any general questions? And we will do the extra credit at the end of the session. Any questions? All right. So in the meantime, if you haven't done it yet, make sure you locate that file so we can look over it. Okay. So I'll give you a few moments to look through your computer files and get out that extra credit with the 100 coin flips, and we'll talk about it at the end. All right. So in the meantime, let's go ahead and go through the lessons for today. All right. Feel free to chat. We're recording. All right. So let's start.
Hi, everyone. In lesson 12, we're going to ask, when do we add or subtract probabilities? We're going to look at OR problems in probability. Now, these rules are easiest when we're dealing with mutually exclusive events, or MEES. MEES is my acronym. It's not official. So what's an example of this? Let's say that we're going to roll 1 die, and we want to look for the probability of getting an even number or a 5 on a standard 6-sided die. Let's say that the event even is event A. Let's say that the event 5 is event B, meaning that event A says that the die will come up an even number, event B says the die will come up a 5. Well, there are a couple of ways that we can do this. We could have done this brute force, like we have before. So in the numerator, we count up the number of ELOs, equally likely outcomes, for which A or B occurs, and divide that by N, the total number of ELOs, which is 6 here. Well, let's go through one by one. Let's go through one by one, and let's see what happens. Okay. So one by one, we're going to go through these 6 equally likely die faces and ask, is event A being satisfied or event B being satisfied? A occurs, remember, if we get an even number. B occurs if we're getting a 5. Okay, so we're going to label the appropriate die faces according to their bars. So one by one. If we roll a 1, is event A satisfied, is event B satisfied, or is neither satisfied? They're mutually exclusive. That means that they cannot both be satisfied. You realize that we cannot roll an even number and a 5 at the same time. Well, if we roll a 1, well, 1's not even, 1's not a 5, so neither applies. I'll put a big green X here. Neither applies. Oops. What about if we roll a 2? 2 is an even number, so event A will apply. So we'll label that with an A. But 2 is not a 5, B is not satisfied. What if the die comes up a 3? Well, 3 is neither even nor a 5, so we're going to cross out the 3. Neither event occurs. What about a 4? Well, a 4 is even, but it's not a 5. So only event A occurs. Now, what about a 5? 5 is not even, but 5 is a 5. So event B occurs. What about a 6? Well, a 6 is even, but it's not a 5, so only event A occurs if we roll a 6. Okay, so in how many of these 6 boxes, for how many of these 6 ELOs do we have a label? When do we have A or B occurring? Well, if we get a 2, if we get a 2, then that means that event A occurs. If we get a 4, event A occurs. If we get a 5, event B occurs. If we get a 6, event A occurs. All right, so for 4 of these 6 ELOs, A or B occurs. So we come up with the fraction 4 over 6, or 2/3. Remember, you don't have to reduce fractions. But there's another way we could have done this. We could have done these event by event. Sometimes that's more convenient. So in particular, this is just a rehashing of this. We could have started by counting up the ELOs for which A occurred. What's the probability that we get an even number? It's going to be 3 over 6, 3/6, or 1/2. What's the probability that we get a 5? What's the probability that B occurs? Well, 1 over 6. And we could just add up these probabilities individually. And why can we do that? Because events A and B are disjoint, or mutually exclusive events, which I'll call MEs. Disjoint and mutually exclusive mean the same thing. All right, and that means that they cannot both occur on the same trial. Again, these are mutually exclusive events, MEs, because you cannot roll a die and get an even number and a 5 on the same trial, on the same roll. They cannot both occur on the same trial. In other words, if one event occurs, it excludes the possibility that the other event also occurs on that trial. So even and 5 cannot come up on the same roll. And there's a basic addition rule for MEs. If A and B are MEs, mutually exclusive events, then the probability of A or B occurring is given by the probability of A occurring plus the probability of B occurring. P of A or B equals P of A plus P of B. So the probability of getting an even number, or a 5, is equal to the probability of getting an even number, which is 3/6. Remember? 3/6. We had 3 A's up here, plus the probability of getting a 5, which was 1/6. Remember? We had 1B up here. 3/6 plus 1/6 is 4/6, or 2/3. The same answers as we got before. So we could go either brute force and figure out which ELOs corresponded to either A or B, or we could have done the events separately, figure out P of A, figure out P of B, and added those results. There are a couple of easy ways of doing this, and both of them worked. We could do a Venn diagram. This is referred to as a Venn diagram, where we have figures and disks representing sets of outcomes. Here's a Venn diagram. All right, so when does event A occur? Event A occurs if we roll a 2, a 4, or a 6. Event B only occurs if we roll a 5. This is not to scale. I realize that disk A should be bigger than disk B, but you get the point. And then if neither A nor B occurs, that happens if we roll a 1 or a 3. They're out here in this space out here, outside the disks. So the probability of A or B occurring is going to be 3/6 plus 1/6 or 4/6. Again, these areas are not to scale. In principle, the areas should be proportional to the probabilities. That should be the case. That was not the case here. But you get the idea. To get the probability of either happening, you add up the probabilities for A and B. P of A plus P of B. All right. So the natural next question is, what happens if the events are not mutually exclusive? What if there are ELOs where both events can occur simultaneously? And that's next time.
Okay, so those are mutually exclusive events. What happens if they're not mutually exclusive? Any questions? Any questions? All right, going on.
Hi, everyone. So what happens if two events are not mutually exclusive? What if they could happen simultaneously on the same trial? So for example, let's say that we're going to roll one standard six-sided die. What's the probability that the die will come up even, event A, or higher than a 2, event B? Let's start by using the brute force method. Let's find the number of ELOs for which A or B occurs, and then divide by n, or 6. I'm going to go up back to our rectangular array here. All right, again, A is the event even, B is the event higher than 2. One by one, let's go through these ELOs, these equally likely outcomes. If we roll a 1, does either event occur? Well, 1 is not even, 1 is not higher than 2, so the answer is no. We cross out the 1. What about 2? Well, 2 is an even number, but it's not higher than 2. 2 does satisfy A, but not B. What about 3? 3 is not even, but it is higher than 2. So for 3, event B occurs. What about 4? Now for 4 is an even number, so event A occurs. But 4 is also higher than 2, so event B also occurs. Right off the bat, we realize that A and B are not mutually exclusive because we have at least one outcome for which both events occur. What about 5? 5 is not even, but it is higher than 2. Event B occurs. What about 6? 6 is even, and 6 is higher than 2. Okay, so for how many of these die rolls do we get A or B occurring? Well, neither occurs if a 1 is rolled, but if a 2 is rolled, if a 2 is rolled, if a 3 is rolled, if a 4 is rolled, if a 5 is rolled, if a 6 is rolled, then A or B, or both, will be occurring. So for 5 of these 6 ELOs, A or B will occur, which means that the probability of A or B occurring is 5 over 6, 5/6. Now, what if we consider the probability of A and the probability of B? What if we had used our old school formula for that? What if we had treated them as MEs, mutually exclusive events? Well, the probability of A occurring would have been 3/6, or 1/2, the probability of an even number, plus the probability of getting a number higher than 2 would have been 4 over 6, or 2/3. It turns out to be more convenient to deal with 6ths anyway. But wait a minute, 3, 6 plus 4, 6 is 7, 6. I know immediately that I got the wrong answer. Why? Well, for one thing, this is bigger than 1. There's no way that this can be a probability. I know I messed up somewhere. And also, there's a more subtle problem. Why is this wrong? Because this ends up double counting the 4 and the 6 as outcomes. We're double counting the 4 outcome and the 6 outcome. So we have to adjust for that if you're going to use a formula. So how do you adjust for that? Again, notice that A and B, these two events, are not me's. They're not mutually exclusive events because both events could happen at the same time on the same trial. Namely, if you get a 4 or if you get a 6, then both of these events will be occurring. And the key thing to remember is that you should not double count the equally likely outcomes. Do not double count the 4 and the 6. So here's the general addition rule. In the case where A and B could be mutually exclusive or not, me's or not, the probability of A or B equals the probability of A plus the probability of B, and then we need this extra term for non-me's. If you don't have mutually exclusive events, you need to subtract the probability of A and B occurring. This is referred to as the intersection of A and B, or more informally, the overlap of A and B. You subtract the probability of the intersection of the overlap. That's where the 4 and the 6 lie. So the probability of getting an even number or a number higher than 2 is the probability of an even number plus the probability of getting a number higher than 2 minus the probability of both happening. The probability of A happening, the probability of getting an even number, was 3, 6, or 1/2. The probability of getting a number higher than 2, the probability of B, was 4, 6. We did this before. Now, 3, 6 plus 4, 6 is 7, 6. But the thing is, we also have to subtract the probability of the intersection or overlap. For how many of the ELOs do both occur? For 2. The 4 put this in orange. I'll put this in orange. Oops. So orange, probably of both. All right. In orange, here's the overlap. The 4 and the 6, they represent the overlap. What's the probability of getting something in the overlap? A 4 or a 6? That's 2 over 6. So we have to take the 7, 6 here and subtract off 2, 6, and then we get 5, 6. That should sound familiar. That's what we got when we did it the brute force way. 5, 6. 5, 6 is correct. So in general, again, if A and B are events that are either mutually exclusive or not, the probability of A or B is the probability of A plus the probability of B minus the probability of both happening, P of A and B. Now, the Venn diagram can help out here, right? Because here's the deal. If you're adding P of A and P of B, the problem is that if they're overlapping, you're double counting this intersection or overlap, A and B. So in order to adjust for that, you have to subtract off the intersection piece once. You have to subtract off one of the colors, and then the other color still remains. We do want one of the colors to remain. It has to be counted, but only once, not twice. By the way, if you want to relate these to the ELOs, so an even number would be a 2, a 4, or a 6. I have to write tiny 4 and tiny 6 here. An even number would be 2, 4, 6. Okay. A number higher than 2, that would be 3, also 4. I'll circle the 4 in purple. Also 5, and also 6. I'll circle the 6 in purple. All right. So P of A plus P of B, but since we don't want to double count the red and circled items, we subtract off the probability of, say, one of the colors here. Okay. And that helps to adjust for the double counting. So again, a key theme: avoid double counting. That was up here. You have to avoid double counting. Do not double count. Now you might be asking, well, how is it that this formula applies even in the event of mutually exclusive events? Well, I'll show you the picture. So here's the picture of mutually exclusive events. Why is this formula still applicable? Well, the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B happening. But wait a minute. If you have MEs, if you have mutually exclusive events, what's the probability of both happening? That, in the case of MEs, is going to be 0. Because there is no intersection or overlap in the case of MEs. There are no outcomes for which both will occur. So the general addition rule is general because it applies to MEs or non-MEs. Because even if you have MEs, mutually exclusive events, that just means that this term is 0. It's still correct, though, the formula. All right, next up. Oh, first of all, as a challenge to you, this is not homework, but what if you had events A, B, and C, which might not be mutually exclusive? It's a much more complicated formula. Here's a hint. This could represent A, this could represent B, and this could represent C. You have the potential for double counting and also triple counting. This is a much more complicated formula. Don't freak out about it, but that's a challenge to you. Next up, we're going to talk about tables, how to find such probabilities using tables.
All right. Any questions before we go on? Any questions before we go on? We looked at some of the formulas behind all this. We're adding and subtracting probabilities in these OR problems, right? The probability of A or B. Any questions?
Hi, everyone. Let's use tables now to find probabilities. Example, let's say that you're going to roll 2 dice, 2 standard 6-sided dice. What's the probability that you're going to get doubles or a 6 on either die? Now, a formula might be a bit too complicated, but consider a 2-dimensional grid or table or array such as this, where we have the red die, the marginals here, 1 through 6, the green die, the marginals here, 1 through 6, and then the entries here correspond to the 36 ordered pairs, the 36 equally likely outcomes, forming the sample space for when you roll 2 dice, red die, comma, green die. So consider using this kind of table and try to consider more clever approaches using some of the warnings I've discussed before. I'll give you a minute to think about this. The more brute force approach using this table, this grid here, and perhaps more clever approaches. All right, you should get the answer of 16 over 36, or reduced, it's 4/9, or about 44.4%. Now, if you use this table here, all right, remember that we get doubles by rolling 1, 1, 2, 2, and so on up through 6, 6. There's 6 outcomes, 6 ELOs that correspond to doubles. Okay. Now, in addition, we have 6 ELOs that correspond to a 6 on red, and then 6 ELOs that correspond to a 6 on green. Now, if you do it brute force, if you count these X's one by one, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Notice I'm only counting the boxcars case once. The 6,6 case is going to cause us some heartache later on. We get 16 over 36, or 4/9. The brute force case, filling out this table like this, may be the best way for you to get at the right answer. If anything, you might be in danger if you try to get too clever. Because here's the deal. The probability of getting doubles is 1/6, or 6 over 36. The probability of rolling a 6 on red is 1/6, or 6 over 36. You think of it as 1/6 as a 1-die problem, or 6 over 36 as a 2-die problem. Likewise, the probability of getting a 6 on green is 1/6 as a 1-die problem, or as a 2-die problem, 6 over 36. So a naive student might just add, oh, well, 6 plus 6 plus 6, 18 over 36. I guess that's my answer, 18 over 36, or 1/2. That's going to be wrong. And why is that? Because they're supposed to get 16 over 36, not 18 over 36. What's the problem? If you do this, you're counting the boxcars case, this guy here, 3 times. Once, twice, 3 times. 3 times. You're triple counting boxcars. So to adjust for the triple counting, you would have to subtract 2 over 36 to make sure you only single count boxcars, 6,6. So again, the brute force case, the brute force approach might lead you to a more accurate result more quickly. Whereas if you're going to try to be clever, you better be very clever and make sure to not double or triple count. When you do this, you do get 16 over 36, which is the correct answer. Next, we're going to look at using a two-way frequency or contingency table where we have a table consisting of counts. Next time.
Any questions? Any questions? Remember, the key thing is to not double or triple count. When in doubt, do the whole check marker X thing that I did. Oh yes, it is a tricky problem. It is a tricky problem. And in fact, it's for the tricky problems where you might just do it brute force. Just draw out a grid and count up the ELOs. All right, any questions? Any other questions? All right, interesting problems. You think they're easy, they're not so easy.
Hi everyone. In this example, we're going to use a two-way frequency or contingency table consisting of counts, where it's not just 1, 1, 1, 1, like we had over here, 1, 1, 1, 1. All right, let's say that you're a tutor. You're a junior, and you like tutoring other juniors. And if a student's not a junior, you don't want to tutor the A students. You'd rather tutor B and C students. So let's say that you're considering the students in a class. All 26 students in the class are passing. They're all getting A's, B's, or C's right now. But they seek tutoring. Now, you, the tutor, you're a junior who likes helping students who are juniors or who are receiving a B or a C, regardless of class status. By the way, there are no freshmen in the class, only sophomores, juniors, and seniors. Based on the following two-way frequency or contingency table, find the probability. So we want the probability that a random student in the class is a junior or it's getting a B or a C. In other words, the probability that a random student in the class is someone whom you'd be willing to help. Okay, all 26 students are accounted for here. I'm not trying to trick you. If you add up all these numbers in here, they add up to 26. Okay, let's go through each of these cells and ask, are these students whom you would be willing to tutor or not? Yes or no? All right. The sophomore getting an A, would you be willing to tutor this student? The answer is, sorry, no. What about sophomores getting Bs? In principle, you'd be willing to because they're getting Bs, but it doesn't matter so much in this case because there are none of them. In principle, though, let's circle the 0. What about sophomores getting Cs, these two people? Yes, they're getting Cs. You'd be willing to tutor them. What about all the juniors? You're willing to tutor all the juniors, the ones getting As or Bs or Cs. What about the 2 seniors getting As? No. They're not juniors, and they're not getting Bs or Cs. What about seniors getting Bs? Yes, they're getting Bs. What about seniors getting Cs? Yes, these 3 you're willing to tutor. So how many students in the class would you be willing to tutor? You can add these up, and you would get 23. So the probability would be 23 over 26. Can you tell me a faster way you could have done this? And we're going to see this in other probability problems. What's the faster way you could have done this? Well, there are 26 students total. There are only 3 students whom you are not willing to tutor. Only 3 whom you would have said no to. And 26 minus 3 is 23. In a way where you're considering the complement first, the probability that you wouldn't tutor the student is 3 over 26. So the complement of that, which is what you want, is 23 over 26. Sometimes subtraction helps. All right, so once again, you're not willing to tutor the 3 students here indicated in red, but you're willing to tutor everyone else. 23 over 26, or about 0.885 or 88.5%. Now, and again, there was the subtraction method you could have used. An easy way of determining that the sum is 23, aside from just adding all of these. You could have gone either way, though. Now, here's the thing. What if you had worked out the marginals? And very often in a problem, you would work out the marginals. So someone might say, hey, I notice here that there are 14 juniors, there are 12 students getting Bs, and there are 6 students getting Cs. Add them up, 14 plus 12 plus 6, that's 32. 32 over 26. No. First of all, obviously wrong. Why? Because this is greater than 1, so there's no way it's even a probability. But beyond that, there's a problem here. What's the problem with just adding 14, 12, and 6 and putting that over 26, aside from this issue? Because if you do that, you're double counting. You're double counting these 9 students. Juniors getting Bs or Cs. You're double counting. That's my warning here. Don't double count. So that's the problem with just adding these marginals, these marginal totals, because you're in severe danger of double counting. Now, what would work? You could take the 32. 14 plus 12 plus 6 is 32, but you have to recognize that you're double counting these 9 students in here. But if you subtract off the 9 students and then put it over 26, 32 minus 9 is 23, and you get 23 over 26, and that would work. So I'm not saying that these marginals here, these row and column totals, I'm not saying that these are useless, but if you use them, you better adjust. Adjust and make sure that you're not double counting or triple counting or whatever. Okay, so there may be more than one way of doing things. We've looked at straight up addition. We've looked at a subtraction method. And we've looked at using row and column totals, provided you adjust accordingly so that you don't double count, all right? Because if you fail to adjust for that, you're going to be doing a similar sin as if you triple counted this boxcars case over here, 6, 6. Make sure you don't double count or triple count. Count the appropriate students only once. All right, next up, when do we multiply probabilities? Those are and problems. Next time.
All right, now before we do that, good time to pause here. Now, I don't want you folks out there gambling, and I'm not trying to train you to gamble, but I think it's appropriate for statistics students to know how a deck of cards works. You should know how a coin works, obviously. You should know how dice work, obviously. And you should know how a standard deck of cards works. So let's do that. All right. Let's do some card problems and problems when we multiply probabilities.
Hi, everyone. In lesson 13, we're going to be multiplying probabilities. That happens when we're doing and problems in probability. Now, these probabilities are most easily calculated for independent events. And we get some good examples with a deck of playing cards. Now, imagine that there's a standard deck of 52 cards, and you pick or draw a card from this deck of 52 cards. Assume there are no jokers. Now, you should know the setup for a standard deck of cards. There are 4 suits, 2 red suits, hearts and diamonds, and 2 black suits, clubs and spades. Each of these 4 suits has 13 ranks. The numbered cards, the spot cards from 2 through 10, and then the face cards, Jack, Queen, King, and then the ace as a high card. Sometimes the ace is a low card. This grid represents the deck of 52 cards in order. It's almost like a freshly made pack of cards you buy at the store before it's shuffled. 13 ranks, 4 suits. Each of the 4 suits has the 13 ranks. Each of the 13 ranks come in 4 suits. 13 times 4 is 52. So 52 cards total. I have 3 questions for you. What is the probability that when you pick the random card from the deck, what's the probability that you pick a 3? The probability that you get a card with rank 3. What's the probability that you get a heart, like the Tin Man? What's the probability that you get a card whose suit is hearts? And finally, what's the probability that you get the 3 of hearts? Okay, that is, what's the probability that you get a card that is rank 3 and suit hearts? Rank 3 and suit hearts. Notice it's an and problem. Remember, in this grid, this cell, for example, represents the 2 of hearts. This represents the 2 of diamonds. This here represents the 3 of hearts. That's the card I'm talking about. What are these probabilities? Well, the probability that you get a 3, one way to look at it is that there are 4 3s in the deck. The 3 of hearts, the 3 of diamonds, the 3 of clubs, the 3 of spades. There are 52 cards total. So you could say 4 over 52, and that would be correct. And guess what? This reduces to 1 over 13. Why does that make sense? It's kind of like the idea of 1 die versus 2 dice. We can think of this as a 1 variable problem. There are 13 ranks that are equally likely. Well, what's the probability you get any particular rank? Say the 3. It's going to be 1 over 13. The probability of getting a jack is 1 over 13, and so forth. Likewise, what's the probability of getting a heart? Well, there are 13 hearts in the deck from 2 through ace. There are 13 hearts out of the 52 cards. This reduces to 1/4. So by a similar reasoning as for the ranks, notice that there are 4 suits that are equally likely to show up on your card. The probability of getting any particular suit is 1/4. The probability of getting a heart is 1/4. The probability of getting a diamond is 1/4, and so forth. Now, what's the probability of getting the 3 of hearts? What's the probability of getting rank 3 and suit hearts? Well, the 3 of hearts is only one card in the deck. There are 52 possible cards, so 1/52. Now, how is this probability, the 1/52, related to these other 2 probabilities? Well, notice that 1/13, the probability of getting a 3, times 1/4, the probability of getting a heart, is 1/52, the probability of getting a 3 and a heart. And that's not a coincidence. This is because of independence. Because as far as probability goes, the rank of the chosen card and the suit of the chosen card are independent. What does that mean? Let's say that you draw a card from the deck. It's still face down. You don't know what it is yet. Now let's say I look at your card and I tell you, hey, your card has rank 3. Does that give you any information whatsoever about what suit it is? Hearts, diamonds, clubs, or spades? The answer is no. It gives you no information whatsoever. What if I tell you, now let's say that you draw another card. It could be the same card. And let's say that I tell you that you drew a heart. You drew the suit hearts. Does that say anything about which rank you picked, whether it's a 2, 3, 4, or so on? Again, the answer is no. Knowledge of the value of one variable gives you no additional information about what the value of the other variable is. So in that sense, these 2 variables, the rank of the chosen card and the suit of the chosen card, are independent. This is a recap of what we did earlier. The probability of a 3 is 1/13. The probability of hearts is 1/4. The probability of a 3 and hearts is the product of these. It's 1/13 times 1/4, and that's because of independence of these 2 variables, rank and suit. The events 3 and hearts are independent events because knowing the rank of a card tells us nothing about its suit and vice versa. The occurrence of one event does not change the probability of the other event occurring. In this case, 3 and hearts. Knowledge of one does not make us update the probabilities for the other. We'll talk about this idea of updating probabilities later. The rank and suit of an unknown card are independent random variables. In a way, they're independent events. Dependent events are, by definition, events that are not independent. So for example, the events 2 and 3 are dependent because if you know that you've drawn a 3, there's no way you've drawn a 2. The multiplication rule for independent events. If events A, B, C, and so forth are independent, then the probability of A and B happening is P of A times P of B. You multiply these probabilities. Likewise, the probability of A and B and C happening is P of A times P of B times P of C. You multiply the probabilities for these events. So for example, what's the probability of getting the 3 of hearts? The probability that your card has rank 3 and suit hearts. Because these are independent events, it's the probability of 3 times the probability of hearts. The probability of getting a 3 is 1 over 13. The probability of getting a heart is 1 over 4. When you multiply these, you get 1 over 52, which makes sense. You can also think of this in terms of a tree diagram. It's like a probability tree. So you've selected a card. It could be one of 13 ranks, and each of these ranks is equally likely. The probability of getting a 2 is 1 over 13. The probability of getting a 3 is 1 over 13, and so forth. The probability of getting an A is 1 over 13. By the way, in other trees, it's possible that these probabilities might be different. So for example, if it came to dice totals, for example, this may be different. Now for suits, each of these ranks corresponds to 4 suits, each with probability 1/4 for hearts, diamonds, clubs, and spades. So if I want to know the probability of getting the 3 of hearts, I would take the probability of getting a 3, which is 1/13, and I would multiply it by the probability of getting a heart, which is 1/4. Again, when you multiply these together, 1 over 13 times 1 over 4 is 1 over 52. So the probability of getting a 3 and a heart is obtained by multiplying the probabilities on these branches. That's the end probability for the entire path, 3 and hearts, 1 over 52. In fact, that's the probability for any card in the deck. Next up, we're going to talk about the idea of drawing multiple cards with replacement.
Okay, we're going to get down to some more numbers. Any questions? Any questions? All right.
Hi, everyone. Let's say I tell you to draw 3 cards from a standard deck of 52 cards. Now, you may need to ask me a key question. When you draw the 3 cards, what do you do? When you draw the first card, you look at it, and then you may need to ask what question. Do you put the card back in which case we're going to be sampling with replacement, as we will in this example, or do you keep the card out, in which case we're sampling or drawing without replacement? Let's say in this example, after you pick the first card and look at it, after we all look at it, you put it back into the deck. The deck is thoroughly shuffled. You pick the second card. So basically, as far as probability goes, it's like starting from scratch. The same probabilities apply whether it's the second draw or the first draw. Then after we all look at the second card, you put the second card back in. The deck is randomly shuffled well. You pick a third card and then put that back in. So sampling or drawing with replacement. Every time you pick a card, you immediately put it back into the deck before you pick the next card, if there is a next card. All right. So draw 3 cards from a standard deck with replacement, meaning that after we draw a card, we place it back in immediately before we draw the next card. So if you're going to do this, find the probability that we draw an ace first, a king second, and a king third. In other words, what's the probability that the sequence of ranks we get will be ace, then king, then king? I'll give you 10 seconds to figure that out. All right. What's the probability your first card is an ace? You draw a card randomly from the deck. What's the probability the first card is an ace? Well, what's the probability of getting an ace? There are 13 ranks, each of them equally likely. So the probability of getting an ace is 1 over 13, 1/13. What's the probability of getting a king on any of the draws? So let's say that you get the ace and you put it back in. You get one of the 4 aces and you put it back in. the deck's randomly shuffled. You pick out the second card. What's the probability the second card is a king? Well, regardless of what happened on the first card, the probability that the second card is a king, well, there are 13 ranks, each of them equally likely. Once again, the probability of getting any particular rank, like a king, is 1 over 13. Let's say you get an ace and a king. You put the second card back in. Deck is randomly shuffled. What's the probability the third card is a king? That's still 1 over 13. Now, if we're sampling or drawing with replacement, again, what happens on the first draw, probability-wise, has no impact on the second draw, which has no impact on the third draw. The 3 draws have nothing to do with each other, probability-wise. We have independence. Because we are drawing cards with replacement, the draws are independent. So whether you're picking the first card or the second card or the third card, the probability situation with the deck of cards is exactly the same. There's no memory. So the probabilities involved with one draw are not impacted by the results of other draws. So going by this rule over here, the probability of A and B and C happening, that's P of A times P of B times P of C. We multiply probabilities. So the probability of getting an ace on the first draw and a king on the second draw and a king on the third draw, these could be events A. Don't confuse A for ace here, but the probability of A and B and C, right? Well, the event A does involve an ace in this case. The probability of A and B and C equals the probability of A times the probability of B times the probability of C. We have independence. It's the straight product. It's 1/13 times 1/13 times 1/13, also known as 1/13 what? 1/13 to the third, or cubed. Exponents come up a lot in these independence problems. By the way, that's 1 over 2,197. It's not very likely. It's about 0.000455. For that matter, what's the probability that you get 3 queens? What's the probability that you get a 2, a 3, and a jack? Each of these probabilities will be equally likely. There are 2,197 ordered triples of ranks. Rank, rank, rank. There are 2,197 ordered triples of ranks, each of them equally likely. Each of these ordered triplets are equally likely. It's the same probability. Look at this possibility tree. You have equal probabilities on each of these branches. 1/13 for each of the ranks on the first draw, and then 1/13 for each of the ranks on the second draw, and then 1/13 for each of the ranks on the third draw. Whichever path you take, including ace, king, king, is going to be 1/13 times 1/13 times 1/13, or 1/13 cubed. So for each of these paths, whether it's ace, king, king, or queen, 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 all right, it's going to be 1/13 cubed. It's going to be the same probability. This. For all of these paths, for all of these ordered triples. All right. Now, in the next example, we're going to ask a similar question. What's the probability of getting the sequence? But how do you think the problem's going to change? What's going to make this problem more interesting? If you are told to draw the 3 cards without replacement, every time you take out a card, it stays out.
All right, let's go to random.org.
Hi, everyone. Go to the website https://www.random.org/playing-cards.
You don't have to. You can do it
On
later.
this site, we can draw cards. So we can draw 3 cards without replacement from one shuffled deck, so that the same card cannot be selected twice or 3 times. So here we got the 2 of hearts, and then the 4 of clubs, and then the 7 of spades, 3 cards out of the 52. But let's say that you want to sample with replacement. There's no option here, but we can draw 3 cards from 8 shuffled decks. That's the closest we can get to sampling with replacement. There are 416 cards, 8 copies of each of the 52 cards. Let's do it. Now here, we get the 7 of hearts, then the 8 of hearts, then the 10 of spades. We did not get any duplicates here, but in principle, we could have.
Oh, by the way, I just noticed something. I think this is putting the cards in rank order. I think the 7 came first, then the 10, then the 8. So you have to kind of watch for that. If you care about the sequence, right? If you actually care about the sequence, then you have to see in what order the cards appear. As they're listed, they appear to be sorted. So I just noticed that now.
Hi, everyone. So let's say that we're drawing the 3 cards from the deck without replacement, meaning that the drawn cards are never returned back to the deck. What then is the probability that we're going to get this sequence? An ace first, then a king second, then a king third. Remember that when we drew or sampled with replacement, we got this probability, which was pretty low. Now, if we sample without replacement, if we draw the cards without replacement and we don't return them immediately, do you think this probability for without replacement is going to be higher or lower than this probability with replacement? Is this sequence going to be more likely or less likely now compared to before? I'll give you 30 seconds to think about it.
Basically, if you throw cards out,
Okay, now before we get to the calculations, we need to introduce an important idea, the idea of conditional probability, which we're going to need if we're talking about dependent events. This is the probability of B given A. Important notation. This is the conditional probability, think updated probability, that B occurs given that A occurs. Now, this idea of updating probabilities is a popular idea, and it's a practical idea among Bayesian statisticians, although it is controversial. There are some purists who don't like the idea of updating probabilities, but I think this is very practical. I was trained as a Bayesian. We're going to talk about medical diagnoses later on. So what is the general multiplication rule for the probabilities of and? So the probability of A and B, that's the probability of A times the probability of B given A. That is, given that A has occurred or is guaranteed to occur. So here's an example. Let's say that you're looking for a date and you go on, I don't know, Match.com or Tinder or something. And let's say that you're looking for someone who is rich and good looking. You're kind of shallow. So then you might ask the dating site, okay, so find me the rich people. And then what do? Are you going to do a brand new search for the good looking people? No, you're going to filter among the rich people who are the good looking people. So the probability that a random person is rich and good looking, according to your criteria, is the probability that the person is rich times the probability that the person is good looking, given that the person is rich. You're conditioning on the person being rich. It's not a brand new search. You're filtering. It's like a filter. Likewise, the probability of A and B and C is like a military scenario. It's the probability of A happening times the probability of B happening, given that A has happened, times the probability of C happening, given that A and B have happened. Again, it doesn't have to be a time sequence, but the idea is that the events that you're conditioning on are assumed to have happened or are guaranteed to happen. So as you build up this calculation for the probability, you're assuming that the previous events have already happened. That's the idea. Now, this is a general multiplication rule. What if A and B are independent? For example, consider the issue of rank and suit. Like, for example, what's the probability that you get the 3 of hearts if you draw a random card from a standard deck? Well, it's the probability of getting a 3 times the probability of getting a heart, given that you've gotten a 3. But now, wait a minute. Let's say that you draw a card, and I look at it, and I tell you that you drew a 3. Well, what then is the probability that you have a heart? Well, I know you have a heart, but I mean a heart on your card. Well, wait a minute. Does the fact that you got a 3, assuming I'm honest, is the fact that you got a 3 relevant? Well, no, it doesn't matter at all, because what's the probability that you have a heart? Whether it's a 3 or not, that probability is 1/4. It doesn't matter what rank it is. So if A and B are independent, like the issues of rank and suit, then the occurrence of A does not change the updated probability of B. The probability of a heart stays 1/4. So that means that the probability of B given A is just the probability of B. The probability of this conditional probability is just the probability of getting a heart. So then you're back to the multiplication rule for independent events. The probability of A and B is just P of A times P of B. This conditional probability degenerates to the basic probability. So this is a general multiplication rule that applies to both independent events and dependent events. All right, now, on to this example. What's the probability that you get the sequence ace, king, king? We need to build up this scenario. So the probability you get an ace first and a king second and a king third, because we're sampling or drawing without replacement, these are dependent trials. The probabilities for these kings over here will depend on the previous probability of getting an A. In fact, the probability of the third king will depend on these previous draws. So the probabilities for subsequent draws will depend on what happened on previous draws. All right, so this probability is equal to the probability of getting an ace first times the probability of getting a king second, given that you got an ace first. We're building up the scenario, times the probability you get a king third, given that you got an ace first and a king second. We're assuming that you're succeeding along the way. Let's say you win if you get this sequence. In order to win, you have to assume that you've been building up the win on previous draws. An ace first, then a king second, and then a king. All right, now what's the probability of getting an ace first? Well, it's the same old, same old. I mean, we have 13 equally likely ranks. The probability of getting an ace first is still 1/13. But for the purposes of this problem, let's say that it's 4 out of 52, which is also correct, 4/52. Because there are 4 aces out of the 52 cards. Now, so that's for this probability. Now, assuming that, conditioned on you getting an ace first, what's the probability that your next card is a king? Now, if you get an ace first, are you a bit more likely to get a king next or a bit less likely? Actually, you're a bit more likely because I'm assuming that the first card you drew was not a king. We're sampling without replacement, and we have a finite number of cards. So if you drew a non-king first, you're a bit more likely that the next card will be a king. Now, what is this conditional probability? I'll do this in blue. Well, we start off with 52 cards. If we're assuming you drew an ace first, what's the probability that you get a king next? Well, how many cards are there left in the deck? 51. And how many kings are still left in the deck? There's still 4. We're assuming you drew an ace first, so I'm assuming that all 4 of these kings are still in play. So 4/51. That's the conditional probability. And then assuming that you got an ace first and a king second, I'll do this in purple. What's the probability you get a king next? Well, how many cards are left? 50. We've already drawn 2 cards. But wait a minute. We've already drawn a king. We're assuming we've already drawn a king. So how many cards are left? How many kings are left out of the 50 cards left in the deck? Only 3. Let's say we first got the king of hearts, right, as our second card. Let's say we got the king of hearts as the second card. Then there are only 3 possible cards, 3 possible kings remaining that you can pull. These over here. So 3 over 50. 4 over 52 times 4 over 51 times 3 over 50. It's like countdowns. As you draw out cards, you're decreasing the denominator by 1. And then depending on what the previous cards are, how many of the desired card, the desired rank, is left. And the answer you'll see is about 0.000362. More interestingly, it's a little bit less than what we got from the first example when we sampled or drew with replacement. This was 0.000455, give or take.
Anyway, substantially less.
Now, why was this lower? Because at first you might be saying, well, wait a minute. If I draw a king, if I draw an ace first, I'm actually a little bit more likely to draw a king. That's true. Notice 4 over 51 is a bit higher than 4 over 52. If you lower the denominator, you're raising the fraction. But wait a minute. Look at this third probability. We're assuming you've drawn a king on the second card. Now, if you've taken out one of the 4 kings, you're a lot less likely that you're going to get another king. So even though you get a slight bump up from here to here, there's a big drop from here to here when you drop the numerator from 4 to 3. That's a big drop there. So it's not as likely you're going to get the third card to be a king if your second card was also a king. That's why this is lower, substantially so. What kind of order triple would be least likely when it comes to ranks? What kind of order triple would be least likely? I would say something like, how about ace, 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 or queen, 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 or 10, 10, 10. 3 of a kind. If you're drawing 3 cards without replacement, then it's very unlikely that it's a lot less likely you're going to get all 3 the same, because then you're going to get big drops in these conditionals. With replacement, it didn't matter. It was 1/13 times 1/13 times 1/13. But without replacement, hey, every time you draw out a queen, you're a lot less likely the next card to be a queen, and so forth. Okay, next up, what's the application for polls?
All right. Any questions? Any questions? Yes, there are a few cards left in the deck, but the key thing is, if you draw out a queen, you're a lot less likely to draw out a second queen. And if you've drawn out 2 queens, you're a lot less likely to draw a third queen. So it's this idea that if you keep requiring the same rank, it's hard to keep the same rank. It's hard to keep the same rank. It's most likely to have different ranks. All right.
Hi, everyone. Here's a key issue with polls: the sampling rule for treating dependent events as independent. When we conduct polls, we sample without replacement so that the same person is not contacted twice. We don't want to bug that person. So technically, the selections are dependent. Now, sometimes to simplify our calculations, we can treat dependent events as independent, and our results will basically be reasonably accurate. We can do this when we take relatively small samples from large populations. Then we can practically assume that we are sampling with replacement, and we can ignore the unlikely possibility of the same item or person being selected twice. So that basically we can treat dependent events as independent, and we can assume independence. We assume independence for practical purposes. And we'd like that because, remember, the calculations were a lot easier, like they might involve an exponent, for example, if we're dealing with independence. With dependence, those calculations tend to be more awkward and complicated, like this countdown stuff we dealt with over here. Independence calculations tend to be easier. So under what circumstances can we apply the sampling rule? Well, when the population is big enough, for our class, let's say at least 1,000, let's say, then even if you're drawing without replacement, you're promising not to call the same person twice. If your sample size is no more than 5% of the population size, then that means that you're drawing a relatively small sample from a large population. And we can assume independence. We can practically treat the selections as independent. By the way, the 1,000 is just a number I picked for our class. Here's an example. Let's say that we look at the popular vote for president in 2000. George W. Bush, the electoral vote winner, won 47.8%, although Al Gore won the popular vote. He won 48.4% of the popular vote. Over 105 million voters voted in that election. That's a lot. I think that's pretty big for Big N. That's a lot. Of those, 3, that's relatively small, way less than 5%, of those 3 are randomly selected without replacement. I mean, the probability of calling the same person twice anyway is minute. Find the probability that all 3 selected voters voted for Bush in 2000. Now, there's no point in doing countdowns. I mean, these percents are rounded off anyway, so there's no point in doing the whole countdown nonsense. We don't have to worry about the 105 million. That's a lot of voters. Okay, find the probability all 3 voted for Bush. So, again, we're sampling no more than 5% of a huge population. We're going to apply the sampling rule, and we're going to practically assume that the selections are independent, even though they're technically not. Since Bush won 47.8% of the vote, remember, we like to convert to decimal when doing calculations. The probability that a randomly selected voter voted for Bush is 47.8%, or as a decimal, 0.478. So what's the probability that 3 random voters voted for Bush, assuming independence? I'll give you a hint. Remember this calculation up here, the ace-king-king problem where we assumed independence. Again, use decimals, not percents. Find the probability that all 3 selected voters voted for Bush. It's the probability the first voter voted for Bush times the probability the second voted for Bush times the probability the third voted for Bush. Each of these probabilities is about 0.478, or 0.478 cubed to the third. That turns out to be about 0.109, or 10.9%. Now, let me ask this question. If a news network says that it randomly picked 3 voters from the 2000 election, and all 3 of them said they voted for Bush, there's a 10.9% chance of that happening, just by chance, assuming that the process was appropriate and we assumed independence. But if a news network claimed that it really was a random selection, what might you ask? Were they really being truthful? Is this too low for us to assume that the network was playing fair and actually selecting them randomly based on a simple random sample? If this probability is too low, then we might really question that network's honesty, at least in this regard. That's an issue for inference later on in the course.
Okay, so that's all for the material for lessons 11. Sorry, for lessons 12 and 13. Lessons 12 and 13. Any questions before we go on to the extra credit? Okay, we have some time for the extra credit now. All right. So remember, so get out your file with your 100 coin flips, and I'm going to tell you how to grade it, how to sort of mark your papers. All right. Okay, so here's how you're going to grade it. All right, our discrimination rule, and it's literally called a discrimination rule. So here's the deal. Some of you actually flipped the coin, or you got the website to flip the coin. Others of you simulated it in your head. You tried to fool me. In a way, you tried to fool me into thinking that you had actually flipped the coin or got the website to do it. All right. Now, here is how I want you to mark your papers. I know some of you emailed me. You don't have to email me or Mark. I'm just doing this to count you folks in this class. All right. Now, look over your papers, right? You have, toss 1 through 10, then 11 through 20, and so forth. I want you to see if there's a run or not, all right? So here's the deal. Here's the deal. Let's say that you didn't have much time, all right? And you just put down 100 H's, for example, or you just put HT all the way through. If you have a situation where if you had given your paper to another person, if the other person could clearly see that you did not flip the coin for real or got the website to do it, then you would assign a P grade to your paper, P for pattern. Don't worry, you're still going to get the points, okay? You're still going to get the points. If anything, I want some P's in our class because then we're going to play American Idol. I'll show you what I mean by that. Now, if you're not a P paper, right? If it's not obvious, if it wouldn't be obvious to someone else that you just got it from your head, you didn't actually do it. Here's how I want you to grade your paper. Look through your paper. If you ever see a run of 5 H's, like 5 heads, or 5 tails, okay? And by the way, this counts as a run. If number 8 is ahead, if number 9 is ahead, if number 10 is ahead, if number 11 is ahead, if number 12 is ahead, this counts as a run, okay? It's okay if you have a wraparound. This does count as a run, okay? So if it's not a P paper, and you got a run of at least 5 heads or at least 5 tails, then put an A on your paper. Your grade is A. Otherwise, put a 1 in your paper. If you think you can fool somebody, right? So if you give a paper to someone, and if the person could not obviously tell, you obviously did not flip the coin. You obviously got this from your head, right? And if you did not get a run of at least 5 heads or 5 tails, put a 1 in your paper. All right. Now, what I mean by American Idol is, what about the P papers, the people with the obvious patterns, okay? The people who got it from their head. Basically, I'm trying to figure out, it's a discrimination rule. I'm trying to figure out which group of people, okay, which group of people made the sequence up in their heads and did not flip the coin or go to the website, all right? So these are the people who did what? They flipped a tail, right? So on the very first coin, if you flipped a head, then you actually flipped the coin or you got the website, random.org, to do it. If you flipped a tail in that first coin, then you got it from your head, all right? So what do I mean by playing American Idol? Here's what I mean. First of all, and by the way, we're approaching time, but see, 9:34, all right? I'll give you a minute to grade your paper, right? Grade your paper a P, an A, or a 1. Look over your 100 coin flips. A P if you did like 100 H's. It's obvious that you didn't flip a coin or get the website. Otherwise, A if you got a run like that or tails. 1 for neither. Well, see, that's the thing. We're trying to figure out who's who. For right now, grade based on runs. See, we're going to figure out who's who. I'm going to try to set the discrimination rule. Okay, so about 20 seconds. Looking for runs. Okay, it's 9:35, sorry. And by the way, you don't have to send me the grades, but I'll tell you what to put in chat, okay? If you just send me the coin flips, that's fine, with their name on it. So again, when you email me for the 3 points, it's just your paper with your name on it and the 100 flips. You don't even need the grade, all right? Some people already did it. All right, now here's the deal, folks. Let's set the discrimination rule. All right, so a bunch of people who got runs, they got the A grade. A bunch of people who didn't get such a run, they got the 1 grade. Now, the pattern people, the people who obviously did not flip the coin for real or get the website to do it. Which group do I think did not flip the coin? I think the people who did not flip the coin got no run. So that's the grading rule. That's the discrimination rule. Where is it? I think it's over here. Okay, let me get my grading sheet again. The coin results. Oh, here it is. Here it is. All right. So now put yourself in this grid. All right. So if you took that first coin and you actually got heads, all right, that means that you went to the website or you actually flipped the coin. That's in red. If you flip tails on that first coin, then you made up the flips in your head. You try to fool me. You tried to simulate 100 random flips. In blue, this is what I said you did. If you got a grade of A, if there was no obvious pattern and you got a run, I think you actually flipped a coin. Because you know what? If you flip a coin 100 times, you expect a run of at least 5 heads or 5 tails, and people don't know that. That's why it's easy to fool people. All right. On the other hand, if you made up the coin flips, all right, then you probably didn't get a run, all right, or there's an obvious pattern, okay? Now, if you're in the top left or the bottom right, that means that my discrimination rule worked well for you people because I made the correct decision. The people who flipped the coin or got the website to do it, I identified them, right? I gave them an A, I identified them. The people who didn't flip the coin for real or got the website, I'm saying you got it from your head and you're in the bottom right. Now, if you're in the top right or the top left, I made a mistake. My discrimination rule did not work. So here's what I want you to put in chat, just for kicks. Tell me which group you're in. Are you in top left, top right, bottom left, or bottom right? This isn't for your 3 points, but I know some of you are confused. But I want to see how well I did. How many of you were in top left? You flipped the coin and you got an A. How many of you were top right? You flipped the coin or got the website to do it and you got a Puro 1. How many of you were in bottom left? You did not flip the coin or get the website, but you got an A. And how many of you were in bottom right? You did not flip the coin for real or get the website, and you got a Puro 1. So in chat, put which slot you're in. Okay, thank you. Yes, yes. And I'm going to count these. All right. So let's see how I did. All right. Okay, so I see. Okay, and I'm not cheating here. I see a bottom left. I see another bottom left. So I made a couple mistakes here. I see a top left. That was a correct classification. Top left, bottom right. That was correct classification. All right, next up. Bottom right. Yes, bottom right. Top left, top left, top left. Okay. 4 top lefts. 2, 3, 4. All right. A bottom right. 3, 4 more top lefts. I'm doing pretty well. 1, 2, 3, 4. A top right. So I made a mistake there. Yeah, computer. Yeah, top right. And yeah. And you didn't, but you didn't get a run. I made a mistake there. All right. Yeah, for the extra credit, again, your name and just the list of 100 H's or T's. That's right. Top left and bottom left. So overall, I think I did pretty well. All right. I think I did pretty well. I'm going to record these. Okay, so we had, oh, okay, so let's see where I have what I have here. Okay. Yeah, I count the top right. I think this is correct. All right. So let's go with this. 3, 6, 9, 11. So you flip the coin and I called it. 2, flip the coin, but I didn't call it. three of you tricked me. Three of you tricked me. All right. So you got it from your head and I didn't catch it. So you maybe figured out that you were going to get a run. All right. Three in the bottom right. So overall, I did pretty well. Now think about what I just said. We're going to talk more about this next week. Remember, if you flip a coin, a fair coin, 100 times, you actually do expect to see a run of at least 5 heads or 5 tails. Okay. So the reason why you weren't able to trick me, a lot of you, is because the reason why you couldn't trick me was because if you try to make it up in your head, a lot of people avoid putting runs because they think it's too obvious. No, for a truly random sequence, okay, you do expect to see a run sometimes, okay? Total randomness does not necessarily imply local randomness. Global randomness does not necessarily imply local randomness, all right? You expect runs. Oh, no. Remember the first coin, I had people flip the coin once to figure out which group you're in, right? That determined whether you actually flipped the coin or made up in your head. All right. So sorry for keeping you over. It's 9:42. Okay. And later on, we're going to do a chi-square test where I'm going to show you, can we prove that my discrimination rule beat chance, okay? Because you could say, oh, Ken, maybe you just got lucky. Well, it's possible that a chi-square test may show that my discrimination rule beats what just random chance might give. This might be better than what sampling error might have offered. All right, so again, for the 3 points, go ahead and email me your 100 coin flips and either put your name on the file or make sure you email it from an account that clearly has your name on it, your legal name, not your nickname like Snooki, okay? All right, so that's it. We're done through lessons 13. Please keep up with the homework. All right. Again, remember, September is a slow grading month. All right. And then October, I'm gonna jam. Any questions? Any questions? I'll stick around for questions if you have any. All right. I'll stick around for questions. Okay. Otherwise, have a good night, and I'll see you. Have a good night. Have a good weekend, and we'll talk on Monday. I'll stick around for questions. Thank you all. I'll stick around for questions. Oh, now regarding the extra credit, you should have gotten the email. If you want, you can email me again. But for the extra credit, well, actually, here's what you can do for the extra credit. Okay, if you haven't done it yet, flip the coin 100 times, or go to that website. I can email you the link. Go to that website, and you should see a run. Okay, that's the idea. Okay, but again, for the 3 points, you just need the list of 100 heads and tails and email to me. Again, if you did it for real, then you should have gotten a run of at least 5 heads or 5 tails. It's highly likely that will happen. If you made it up in your head, I'll bet you didn't do that. Okay, people don't expect those kinds of runs. We're going to talk about that. Oh, that's right. Yeah, I already got it from you. Yeah. All right. But the key thing is the lesson. You do expect a run. All right, go ahead and email me. All right. Questions? Any questions? All right. So I'll give you another 30 seconds if anyone wants to chat or talk. All right. Okay, any questions? Any questions? All right, so have a good night, everyone. All right, take care.